Hello, my name is Nufaiza binti Hartono and I will explain to you what is buck converter. So buck converter is a DC-DC switch mode power supply that is intended to lower the input voltage of an unregulated DC supply in order to stabilize lower output voltage. So as you can see, the simplified circuit diagram in the slide, it shows how current flows through the circuit during a switching event of a buck converter. Next, as you can see in the slide, it shows the differential equation. Second derivative indicates that the system is second order. So this derivation is made from its voltage and current relationship through Kirchhoff's voltage and current laws. So this analysis leads to a second order differential equation. Then for the transfer function, as you can see the equation inside the slide, this transfer function of the buck converter which relates output voltage to input voltage has a second order form because it includes two poles associated with the inductor and capacitor. There are two types of buck converter. The first one is open loop buck converter. In this buck converter, there are two modes, which is the first one is mode 1 when the switch is on. So when the switch is on, the current flows through the inductor, storing energy and building voltage. So the diode stays reverse bias, isolating the output, and the output voltage depends on the switch duty cycle. The next mode is mode 2, which is when the switch is off. So when the switch turns off, the inductor maintains current flow, forcing the diode into forward bias. This allows current to flow to the output capacitor and load as the inductor discharges its stored energy, supplying power to the load. Next, the second type of buck converter is closed loop buck converter. So in this buck converter, the output voltage is monitored and compared to a reference, which means there is a feedback loop. So the resulting error signal adjusts the converter to maintain the desired output voltage. In this buck converter, there is PI controller which minimizes error to maintain target output voltage. So P means it is to correct base or current error. Meanwhile, integral is eliminates steady state error by integrating past error. So the output of PI controller sets duty cycle for PWM, which is pulse width modulation. So this PWM then adjusts switch timing, controlling energy transfer to regulate output voltage.
Hello, my name is Virashni and I'll be explaining about how the open loop buck converter will work and how to prove it through Simulink and MATLAB simulation. Looking at the design, we have made a buck converter using pulse generator, IGBT, diode, series RLC branch, voltage measurement, scope, and a DC voltage source. We also have implemented some values to be used for each of the components, which are 10 ohms of resistor, 100 millihenry of inductor, 25 microfarad of capacitor, and an input voltage of 100 volts which will be supplying to the open loop buck converter. Next, we will see the simulation of the buck converter. After designing the open loop buck converter, the output voltage or the step response of the buck converter can be observed from the scope. It can be seen that from the graph, we obtain an output voltage of 60 volts from the supplied input voltage of 100 volts. So it can be proved that the buck converter is indeed stepping down the 100 volts input voltage to 60 volts of output voltage. After looking at the simulation of the open loop buck converter, we can relate it back to the control system topics that we have learned. For the first topic is that we can relate it to time response, where we can find the poles, zeros, damping ratio, and natural frequency. From all the information that is obtained, we can conclude whether the system is either overdamped, undamped, underdamped, or critically damped. Now let's look at the system that we have created. In MATLAB, we can find the poles and zeros of the second order system from the transfer function, which can be obtained from the circuit using the appropriate formulas. Looking at the pole zero map, we can see that the system has two poles and the poles are on the left half of the real axis. Damping ratio and natural frequency also can be found from the MATLAB providing the proper coding made. From the results, we obtain that the damping ratio is 3.1623, and from trusted sources we know that if the ratio is more than 1, the system is overdamped. So we can conclude that from the time response analysis, we found that the open loop buck converter is overdamped since the poles are on the left half plane on the real axis and the damping ratio is more than 1. And we can also see that the step response is from the MATLAB is exactly the same as the step response obtained from the scope in Simulink. The second topic that we can relate to is stability. As we know from the time response, we can find the poles and zeros of the transfer function using the right formulas. Now looking at the MATLAB results we obtained, that from the system we'll have two poles and it will be on the left half plane. From the topic stability, we know that if the poles are on the right half plane of the system, it is considered as unstable. But from the system that we made, we can see that the both poles are on the left half of the plane, deducing that the system is stable. Last but not the least, the topic that we can relate to is frequency response. In MATLAB, with the right code, we can obtain the Bode plot, which has the phase and magnitude graph as well as the Nyquist plot. From the MATLAB, we can find gain margin, which shows the amount of additional gain that the system can withstand before becoming unstable. Greater gain changes can be handled by the system with a higher gain margin without running the danger of oscillation or instability. We found that the gain margin is infinity, meaning that the system's ability to handle greater gain change is high since it is infinity. Next, the phase margin is 35.103. This indicates how close the system is to instability. Since it is 35.103, it is close to instability. Following is the gain crossover frequency, which helps to identify phase margin at the moment where the system's gain is crucial for stability, enabling to evaluate the system's stability immediately, where in our case it is infinity. Finally, phase crossover frequency makes it possible to calculate the gain margin and determine the amount of gain margin that is available at the critical phase shift, which is 5.754 to the power of 3.
For this closed-loop buck converter, the difference is that a feedback is added with a PID. The function of the feedback is to ensure the error can be detected and the system will try to minimize the error. PID, which is part of the feedback, has also been added and the values have been stated in the slide given. Given as the final output of the step response from the simulation with minimal overshoot and time response. This has indicated that the PID values have been adjusted to get the ideal output that is supposed to be get. The step response formula has been applied since this is a closed-loop system, and the above plot shows that the proportional controller compared to the open loop, which is reduced both the rise time and the steady state error, and the overshoot is increased and the settling time is decreased by the small amount. For the frequency response, the gain margin has indicated a high value, which means the system is stable and can manage greater gain change. For the phase margin is very low, which suggests low stability buffer, and this process is when the PID controller is needed to minimize the error. All poles are at the left half plane, leaving only one pole at the imaginary axis. This means that the system is marginally stable. Stability is validated since the Nyquist plot doesn't encircle the critical point, and the phase margin in degrees shows that it is above 45 degrees, which indicates stability, and the phase crossover frequency indicate that the value is around 1/2 of the system bandwidth, which indicate the real ideal value. Now, we have designed a closed-loop system with no overshoot, fast rise time and no steady-state error, and a well-tuned PID controller shows a minimal overshoot, appropriate rise time and stable settling, confirming that the controller effectively managed the system dynamics.
That is all from us. Thank you.